Hi everyone, today we will learn how to train a perceptron to classify images. Here's the code, and we can train a perceptron with less than 100 lines of code using the scikit-learn and the numpy package. We will use this perceptron to distinguish between images of dogs and frogs. But before we jump into the code, let's take a look at the theory behind a perceptron. Here on the left, we see the most simple version of a perceptron possible. All the way on the left, we have what is called features. Features are the input to our perceptron, and they can be anything that can be expressed by numbers. Since we are trying to classify pictures, our features are the pixels of the images we want to classify. Each x value represents a pixel, and each pixel contributes to the output with a certain weight. Finally, at the output, a so-called output function is applied that decides which class an object belongs to. For example, values larger than 0 could be considered dogs, and smaller 0 could be considered frogs. This perceptron is so simple, we can express its output with a single equation, where each feature has a single linear term made up of the feature and its weight. Now you might be wondering, this is supposed to be a neuronal network, right? This is a machine learning thing. So how does this perceptron learn anything? The secret lies in the weights. Learning means to adjust the weights, and this is where things get a little more complicated. Learning in this sense is a linear fitting problem, and there are many different ways to solve this problem, with each way having certain up and down sides. The exact math of these is beyond the video, but the best way to think about this problem is to imagine some images coming into this network. When we teach a network, we give it a bunch of images, which we call training dataset. This training dataset is already perfectly classified, usually by a human, so we know what is on each image and we tell the computer. When the network starts, it will randomly initialize the weights and will make a lot of mistakes. Then it changes the weights in a certain direction and checks if it makes more or less mistakes. If it made less mistakes, it will continue in that direction. If it made more mistakes, it will change direction. And it will continue this process until the training data set is separated good enough. But there is a problem with this simple perceptron. The simple perceptron can only separate classes that are linearly separable. That is because the network cannot distinguish complex features. Enter the multilayer perceptron. By adding what we call hidden layers, the network can separate increasingly complex features. The hidden layer is simply another layer between the feature layer and the output layer. Each neuron in this hidden layer receives input from all neurons in the previous layer, the same way the output layer received from all input neurons in our previous example. These hidden neurons sum up the input they receive and send it to all neurons in the next layer. In this example, there is only one hidden layer, so the neurons send their output to the output neuron. But there's one additional twist. The hidden neurons only send their output to the next layer if they have crossed a certain threshold function. So if their value is too small, they don't send anything to the next layer. You may have heard about deep learning, and a lot of the hype around deep learning is essentially about these hidden layers. Actually, the term deep refers to the amount of hidden layers. The more hidden layers, the deeper the neural network. But going deeper is not always a good thing. Now let's look at the code of our perceptron in Python. Most of our code is about loading images and pre-processing them. I will talk about the details of loading the images and the pre-processing in another video, but essentially we use the CIFAR10 dataset, which is specifically made to test machine learning algorithms. Check out the link in the description. We load the images from this dataset, and then we select 5,000 images of dogs and 5,000 images of frogs for our training dataset. We also select 1,000 images of dogs and 1,000 images of frogs for our test dataset. We will need the test dataset to check how well our network learned with the training dataset. The multilayer perceptron itself is created on line 89, where we call the MLP classifier constructor. The reason why constructing this entire network is so easy is because the great people that built the scikit-learn package implemented the multilayer perceptron for us. So we simply import the MLP classifier at the top of our script, and then we can create the perceptron as we like. This perceptron has two hidden layers. The first one has 1536 neurons and the second one has 768 neurons. The solver parameter specifies the algorithm we want to use when training our network. In our case, we use the LBFGS algorithm. The random state parameter is just a random seed that guarantees that we get the same result whenever we run this script. After we created our perceptron, we actually have to train. And we do this with the fit method on line 92. As I explained before, learning means to fit the weights of the model to the dataset. That's why this method is called fit. To the fit method, we give our training dataset and the labels. The labels tell our network if an image shows a dog or a frog. After we trained our network, we have to test its performance on the test data using the predict method. With the predict method, each image in the test dataset is classified by the network according to what it learned while fitting. Finally, we simply calculate the percentage of correct predictions to get an idea of how well our network did. Our network got 79.85% correct. So is this good? First of all, it is well over 50%, which is the percentage our network would get if it was untrained and simply guess. So our network certainly learned something, but with other types of networks, people have achieved 11 to 8% error rates. On this dataset, looking at all classes of the dataset, not only dogs and frogs. So we are certainly a little behind, but in the end you have to look at the real-world application of your network if you want to decide if it's good enough. That is one thing about neuronal networks. Building them is really easy these days. But the hard part is to prove that your network does the job good enough with the data available. Good enough can mean very different things depending on the job. Now I will make some more videos on this network. Specifically, I want to explain how images are loaded from the dataset, how we process the images, and why the pre-processing is important. And finally, I also want to take a look at the parameters on the network before and after it is trained to see if we can get anything from that. See you then.